I am Chiara from the Non-Analysis group at Imperial College London. Today, I would like to present our recent paper that came out in ACS Nano. The title is Selenium-substituted Non-Fullerene Acceptors, a route to superior operational stability for organic bulk heterojunction solar cells. So non-Fullerene acceptors are one of the most promising candidates for viable and highly efficient organic solar cells, and in particular one of the most well-known and used molecule is ITIC. In this work we are characterizing some new non-Fullerene acceptors using the substitution of selenium in the structure of ITIC in the core of the molecule, and we are substituting selenium either in the inner or outer position in the core, and we are combining this, as you can see in this figure, we are combining this with the presence or absence of a methyl group in the end groups. So we are characterizing 4 new non-Fullerene acceptor molecules. So one of the most important findings of the paper, as shown very well in figure 1, is the impact of selenium substitution on the stability of devices. So here we assess the lifetime of devices. We continuously measure the efficiency of the devices under operational conditions in light for almost 500 hours, and we compare the lifetime of devices, and we see that the substitution of selenium in the outer core region is strongly improving the stability of ITIC, and for the combination of outer selenium substitution and methylation, we preserve 95% of the original power conversion efficiency. So this is a very promising finding, and over the paper we try to understand the origin of this superior stability. So we identified different mechanisms responsible for degradation of performances in light, and in particular we found that processes of changes in the structure of the molecules, donor and acceptors, are happening at the same time as a reorganization of the morphology in the blend. So, as illustrated in figure 3, we see quenching in the Raman peaks in the vibrational modes, and also a bleaching in the chromophore, so a decrease in the absorption. In particular, this is related to the conformational changes in the polymer, which is, for example, twisted, and it loses its conjugation in light. But also at the same time we observe a very strong increase of the photoluminescence, and this is a signal of segregation, phase segregation, so a morphological reorganization in the blend. Yes, so these processes are happening in all the blends, in all the materials, but for selenium out methylated case, these are strongly reduced. So we try to understand what is so special about selenium out methylated, and we found that this molecule has a higher crystallinity, so the molecules have stronger intermolecular interaction that are tuning the crystallinity, and this is preserving a positive and optimized morphology in blends, also under prolonged light exposure. And also in this molecule, in these films, we are observing a very small presence of drop states, and by computational calculation, as shown in this figure, in figure 6, we see that selenium methylated has a specific distribution of charges over the molecular structure, thanks to the combination of the larger orbitals of selenium in the outer part of the core and the presence of methylation in the end groups. And this is tuning the charge localization over the molecule to give more possibilities to interact with other molecules in the solid state packing, and to stabilize the overall morphology of the neat material and the blend. One of the most interesting techniques I used for this paper is the transient absorption spectroscopy, thanks to the collaboration with the ultra-fast optoelectronics group in the chemistry department at Imperial College. And with this technique, we were probing the recombination of excited states in blends, and we found very interestingly that the outer selenium NFAs have a much longer recombination time, so a much longer carrier lifetime in blends compared to the inner selenium NFAs, and this indicates a wider dimension of the domains in the blend, and so a more optimized morphology for the OPV behavior. So the main message is that we have powerful synthetic tools to improve the stability of non-Fullerene acceptors, and this is a very important challenge to embark in for the real commercialization of organic solar cells. So in this case, we demonstrate that the introduction of selenium in the structure of the non-Fullerene acceptors is really promising to extend the lifetime of organic solar cells. So if you want to take a look at our paper, please find the link below, and thank you very much for listening.